Welcome back, friends. After doing the calculations of full load amperes and short circuit currents, that's also called as a through fault current, we will calculate the secondary current corresponding to HV and LV sides. So we will see how much will be the current in the secondary side of each CT if the primary current is known. So we know here that we have calculated the full load amperes at HV side are 437.4 amps. So this is the full load amperes. And we are doing these calculations at the nominal tap. And the tap that as I've shown you at which the voltage is the rated voltage 132 kV and the low voltage side is 33 kV. So we are doing our calculations at the nominal tap. So what we are doing here, we are basically dividing the full load amperes by the CT ratio 500. So we are getting secondary side HV current as 0.875 amps. So it means that at the rated current at the nominal tape, the ratio of the CT secondary side current will be equal to 0.875 amps, and in the same way the LV side CT secondary current can be calculated. So this is the LV side full load amperes, which is 1749.5 amps. We have to divide it by the CT ratio, and CT ratio here is 1800 by 1. So we can see here the CT ratio is defined here on the top in these calculations. So the primary CT ratio HV side is 500 by 1. This is the current transformer, and the current transformer at the low voltage side is 1800 by 1. So if you want to calculate the CT secondary current, you have to divide it by the ratio. So in this case, you can see here, so we have a transformer, for example. This is the transformer. This is star side, this is delta side, and this is the CT, and this CT is 500 by 1, and LV side CT here is 1800 by 1. So 500 by 1 means 500 ampere current is flowing at the primary side. At the secondary side, you can see here, this is the relay here, this is the relay, and this CT is connected to the relay. So the CT input is connected to the relay, and the relay there are the elements, current sensing elements, which will measure the currents connected to the relay 87 differential relay. So here we have shown that the current at nominal current at the HV side full load current is 437.4. So you can see the current at the full load amperes is 437.4 amps, and LV side current is 1749.5 amps. So you have to divide it. If 500 is flowing, the secondary side current will be 1 ampere. If 437 is flowing, you have to divide it by the ratio here. So the ratio is CT ratio at HV side is 500 divided by 1. This is equal to 500. So for example, if the transformer is 500 by 5, the ratio will be 500 divided by 5. The CT ratio in this case will be equal to 100. So you have to divide it 100 if you want to calculate the secondary current. But in our case, the CT ratio is 100 by 1. So if you calculate these currents, you can see you will get 0.875 amps here, 0.875 amps at the HV side, and 0.972 at the LV side. So these are the two currents that you're going to get. So further note, there is a difference between HVCT current and the LVCT current. So it means that you need to calculate the matching factor. So you can see even at the balance condition, after putting the CTs, there is a difference in the HV and LV current. It means that there will be a differential current if we do not put any matching factor or any factor in the numerical relays. So nowadays in the numerical relays, you just need to put these factors, you need to put the factor groups But in the previous relays, where we have electromechanical relays, we have to use the matching CTs to compensate the ratio and the phase shift errors, to compensate all these errors or these shifts. So for the ratio correction, so we will put K amps HV-CT. So you will use this formula: CT ratio HV side, HV full load ampere at nominal tip. So the CT ratio is 500 divided by 437.4. So K amp HV-CT will be equal to 1.143. So in the same way, you have to do the calculations for the LV-CT correction factor. So it is equal to CT ratio of LV divided by LV full load amperes. CT ratio of LV is 1800 divided by 1749.5. So K amp LV CT is equal to 1.29. So we have both correction factor calculated for HV side and the LV side. So hence corrected HV CT current ratio I1 is equal to 0.75 into K amp HV CT. So if you multiply this factor 0.75 into correction factor, you will get 1 per unit. In the same way, it means that this is the current which is flowing at the secondary side. So when you multiply it with this factor 1.143, you will get the 1 per unit, and the relay will multiply this correction factor to the actual secondary current, and it will get 1 per unit at the HV side. So we will see the LV correction factor. So LV correction factor, you can see LV current at full load ampere at 1800/1 is 0.972 amps. This is secondary current which will be feed to the relay at the LV side. So if you multiply it with the LV CT correction factor 1.029 amps that we have calculated, again you will get the 1 per unit. So you need to feed these two correction factors in the relay, and then relay will then automatically will multiply the secondary currents to these factors to calculate the differential values. So it means that using these two factors, we have successfully corrected the ratio error at HV and the LV sides. So now after completing this, next we will see the tap position HV side current calculations. Welcome back. In this section we will do the calculations for HV current at two different tap positions. So we will see the HV side current at the tap position when the voltage is increased by 10%, and when the voltage is decreased by 10%. So if you see, now we will calculate the HV tap calculations, HV current calculations at plus 10% of the voltage tap at the HV side. So here you can see this is the formula. So you have to use the same formula. S is equal to 100/3V into I. So this is 100 MVA divided by 100/3, and this is the voltage at 10% of the tap. So we have calculated the voltage at 10% of the tap, that is equal to 1.1 into 132. So it's equal to 145.2 kVs. So the voltage current at the HV side at plus 10% at the tap is 397.6 amps. So if you multiply this with the CT ratio, so this is the primary current. So you want to calculate the secondary current, which is after the CT. You have to divide it by CT ratio. So this is, you have to divide it by 500. So this is the secondary side current, that is 0.795 amps. So this is after the current transformer, when the primary current is being reduced by a ratio of 500 amperes. So now we will multiply it with the correction factor. It should come, if everything is fine, 1 per unit, but because of the error introduced by the tape changer windings, so when you multiply it with the correction factor 1.143 into 0.795, you can see now the relay will sense this as 0.909 per unit. So it means that there is an error in the calculations which is almost equal to 10% because of plus 10% of the tape changer windings. So in the same way we will do the calculations for the minus 10% tap for the HP sides current calculations. So we have to use the same formula, and that is S is equal to 3V into Y. Here we will put the voltage uh, um, which is at minus 10% tap, which is 118.8 kVs. So you will get the primary current which is 486 amperes. So now you have to divide it by the CT ratio. You will get 0.972 amps. This is the secondary current at the HV side at minus 10% of the tap. So you need to again multiply with the correction factor 1.143. So this is the reading that relay will get, and you can see the here almost 11.1% is the error in this setting available. So now we will see the differential current at the normal loading with extreme taps. So we will see how much is the difference of a current that is being produced at the loading. So you will see differential current at 10% of tap is equal to I1 minus I2. Okay, so this is the differential current that is being produced. Even everything is fine. If you put the tap at plus 10%, so you have to divide HV current minus LV current. So we are using per unit calculations here, so you don't need to use actual primary current, so we will use a per unit values here. So this is 0.909 per unit minus 1, so it's equal to 0.091 per unit. So this much is the differential current the relay can have even after providing the correction factors, and this is because of plus 10% of the tape changer windings. So in the same way, if you have a tap at minus 10%, so you can see here this is equal to I2 minus I1 minus I2, and you can see here again the tap differential current because of the tap at minus 10% is equal to 0.111 per unit. So this much is an error, so we have to keep in mind this is differential current, and we have to use this one for our differential setting calculations. Thank you very much.